Are y'all able to see my screen?
I can see it.
Okay. Cool, we'll get started then. So today we're just covering General Chemistry 3 and the topics we assigned in that. Today is mostly acid and bases. So like we said in the past, email us at info@premedpeers.org if you have any questions, or you can Slack us. And we're recording this session, so you don't have to take notes or anything, and the slides will be up also. So we're going to go over the homework and then do some content and warm up and then go over the practice passage. And these are the things that we will be covering in our content today. So do you guys have any specific homework questions that you had? And we can go over it right now. Okay, if not, Isabel is going to go over some of the content now.
Sim, do you want me to share screen or just give me one sec? Can you guys all see my screen?
Yep, we see it.
Okay. So, this week we talked about majorly acid and bases, and just to kind of go over the types of definition that you will encounter. Let me see. So, I found this article, and it talks about metal-induced histidine deprotonation. Just by glancing the bolded side, which is on your left, the abstract, really quickly, including the title, can anyone tell me what is the definition of the acid bases in terms of the histidine that the article discussed? And type in the answer if either A, B, or C for Arrhenius or Bronsted-Lowry or Lewis acid bases, if you can. I'm gonna give it a few moments until 20 more seconds probably.
Someone said B.
Someone said B. Okay. If you just joined, we are going through some of the warm-up in terms of the definition of acid and bases. And I found this article, and it talks about the metal-induced histidine deprotonation. And the question is, which definition of acid-basis form of histidine does this article explore? We're just gonna have people type in their answers. If you want to explain, Emil, if that is okay with you, or if not, that is also fine too. Okay, I'm gonna give it 5 more seconds. All right. So this article talks about the Bronsted-Lowry definition of acid-basis form, and really you don't really have to kind of think about what histidine really is, because if you catch the word protonation states of histidine, then it should comes to you that only one of them between the definition, only one of them, which is the Bronsted-Lowry, talks about the protonation state in terms of the acid and bases. And here, how I kind of relate them one another. Arrhenius came first, and then we have Bronsted-Lowry talking about the proton acceptor, proton donor, and the Lewis talks about the electron donor and acceptor. And the way that I kind of I could not say that is to kind of memorize, because as I'm kind of mentioned from the very beginning of the course, I would encourage you guys to kind of relate things, understand how one concept relate to another, instead of really just memorizing, okay, proton donor is the acid, and then proton acceptor is the hydroxide. So in this case, I will always go back to the very beginning, Arrhenius, where acid always gives the hydrogen cation, and then you have the hydroxide and anion being the basis. And then the Bronsted-Lowry, the way that you memorize which one is the donor, which one is the acceptor, just think back which who gives the hydrogen cation, which is the proton, right? And then if you think about the proton themselves having the positive charge, of course, in the end of the day, they're gonna accept electron, right? So then the role kind of reverse, with acid accepting the electron, whereas the basis donating to electron. And the other kind of key terms right here, amphoteric and amphiprotic, I kind of highlighted here because they're also important in biochemistry. Another thing that I kind of wanted to review with you guys is about Arrhenius equation, which I didn't kind of go over last week. Sometimes it appears, I definitely have seen it during so many practice exercises, and really the only thing that I kind of understand through this equation is the left with the Arrhenius, the A, which is the frequency factor, also called Arrhenius factor. It is really how the probability of correct orientation of those reactant colliding to each other, leading to a really forward reaction, a successful reaction in that case. And then on the other side, with the E exponent, you have the probability of collision, where you have a bunch of terms over the factor, negative E, which is the activation energy, over the RT. And I'm not gonna be like going over about memorizing this, but the key important thing is just to understand how lowering activation energy, manipulating the temperature really affects the rate constant, which is meaning the reaction rate. So going back to this article, how does the superoxide reductase work to enhance reaction rate? Because in this article, it talks about the superoxide reductase. And again, focus on the question and how it relates to what I just talked about, and in relation to the answer choices that is given right here. You don't have to be afraid that there are terms that you don't understand, but understanding what are those terms really means in the article. For example, what I was talking about histidine is talking about histidine as an acid basis. You may not know about histidine, but you definitely know acid basis and protonation state. So in here, we talks about superoxide reductase. And I will give you guys probably 30 seconds more to answer the choices and in the chat.
We got a lot of B's and A's.
Okay, I got it. I think most people answer A, and which is correct. Um, this is what I was talking about, relating some of these terms and what it means in the equation in related to the um, reaction rate constant reaction right here in the Arrhenius equation. Really, when you reduce the activation energy, because the factor right here on the exponent, it is negative, so the lower the activation energy becomes, it is gonna be smaller E overall. No, it will become a larger E overall because the factor itself is negative. And then by putting it into the denominator, given that the factor is negative, you will be getting a greater rate constant and therefore a faster reaction rate. Here, superoxide reductase, what it really means, it doesn't really matter, because the whole point here is just talking about superoxide reductase as a catalyst. And as long as you know what catalysts do, in terms of affecting the reaction rate, that is sufficient enough. Nothing in MCAT is going to test you, oh, how does superoxide reductase really arrange certain things. It's always asking you about something that you actually know, and we kind of go over and over. Those are the main concepts. And another thing that I would kind of have you guys think about, I'm not going to go into details, is how does orientation favor reaction? And that would be something that you might encounter in your biochem study as well. But here I'm just gonna be kind of highlight that it's gonna be affecting the Arrhenius factor, the frequency factor, because if you kind of get the right orientation, it will kind of speed up the catalyst rate. And then the next thing is really the constant. You always see a bunch of constants since last week after the equilibrium constant. So then here we have Ka, Kb, Kw, but what are really the differences? So what I wanted to have you guys remember is to think about what we learned last week, the equilibrium constant, Keq, and Keq is basically the concentration of the product over reactants, the concentration of the other reactants. And if you put each of the thing, if you just write down how acid kind of solvate in water and giving the proton and the respective species, you kind of get the same thing. Like K, KW, KB, they kind of have the same thing. But then the only thing that I would tell you guys, which is a little bit confusing perhaps to some of you, is why there is no denominator in the KW. I wonder if anyone know the reason behind of why we do not have a denominator of the concentration of H2O in the denominator. If you type yes that you don't understand, then I will talk about it. If no, then I'm gonna skip it, okay? And another thing is pH. Oh, so some of you guys say yes, no problem. So the reason why H2O is not in the denominator is, yes, Sarah, you got it. It is a liquid in a sense. And also, if you think about anytime if you add salt, it would be in a solvent, right? And that solvent is most of the time water. But you can't really dissolve water in water because the concentration itself is entirely water. And therefore you don't really have a concentration of water in that case, because it will since just be 100% purity water. So therefore that concentration kind of goes away in a sense because it's just one. And if you don't understand, I will kind of go over, but I wanted to go through the material real quick so that we can go into the passage. And then we have pH. POH, pKa, and pKb. And those are equally confusing. At first, for me, I mean. But the only thing is, I always try to summarize into one concept. What is the main concept that I need to remember? And the main concept here is given that how you calculate something that is px, and the way that you calculate is always going to be the same, is the negative of log the concentration of that species. And if it is a constant like Ka, Kb, then you just put it in, do the log, do the negative sign, and boom, you got the answer. And how you kind of differentiate the pH and the pKa is you remember that K is stand for constant, and it is something that it happens in an equilibrium. However, the state of any liquid, they may not be immediately at their equilibrium. If the concentration of that proton in that solution is too high, higher than is Ka, then it's gonna be likely to be protonating it, because now you have more of that proton ion in your solution. So remember the differences. The pH is talking about the state of that solution, whereas the Ka is as that solution approach to its equilibrium, where should it be? Given that that acid in that solution can be various things like sulfuric acid, phosphoric acid, any kind of acid. And another important equation here to relate those two is really the pH and the pKa. And if you look back up there with all the constant, you will notice that they kind of just break up the Ka, like separating the concentration of proton away from the anion over the acid in its protonate form. So now we talk about the strong and weak acid and bases, and as always, from the very beginning of the class, I mentioned that try to simplify everything if it has a complete opposite side of the things. So here, back then, I kind of talk about, what was I talk about? I talk about the energy state when the proton absorb energy being excited, the electron being excited when they absorb the photon, and then they emit back that photon. So that is the opposite kind of reaction. And we have that here, which is the acid, and the opposite is the base. So in the case that we have acid, and how it makes a stronger acid is really the more stable that an ion be, then the more likely that it will stay dissociated, right? And the definition of strong acid is really just that it is completely dissociated in solution. So what makes a very stable anion? It is the electronegativity, which we talked about in the session 1. The ones that are very electronegative tend to be either NOF or the ones on group 7, because they have abundant electron in their outermost shell, and they have a very strong nucleus to kind of pull everything in. And another thing that we also talk about is the resonance structure. The more resonance structure and the more stable it is, then it allows it to be a more stable anion as well. And you also have to think about, sometimes they give you different options, and they will switch some component, certain element in a similar structure kind of molecule. Then you have to kind of compare that whether there is electron donating species nearby. If they are withdrawing, competing for that electron, then that anion wouldn't be very stable. And what happened is that those ones that I kind of boxed in blue, happen to be the one that is kind of wealthy in their electron. However, when you go to nitrogen or oxygen, they're very thirsty for that electron. They will kind of try to pull it apart from the other guys. So you kind of have to think about that. And again, on the opposite side, you kind of flip the coin. You flip everything. Um, the stronger the basis is the more stronger that cation be. And then everything about the cation will be completely opposite. Do you want a very strong electronegativity? Probably. Maybe, maybe not, you know. And but then the important thing is you want something to pull that electron away, because then you will create that positive charge, and that's how that positive charge can be stabilized. How then the weak acid and bases kind of come between in the middle, so it can be going to the hydroxide, donating that hydroxide anion, but it also goes to the other way to give that proton. Whereas that anion and cation formed is not very stable, it depends on the environment, and that is why that pH and or pOH value kind of come into place. And you have to think about what environment, what kind of things that is surrounding, that it would influence the direction of that reaction be. And here I want to emphasize what we go over last week about the Le Chatelier principle. And the way that I always think about is which one has more stronger species, like, and more abundant species, either from the reactant or A here on the left or B on the other side. If they have a stronger army, a better species, and more abundant, they're likely to push that reaction to one side or the other. And this is kind of the case when you encounter biochemistry question, and which sometimes they relate it a lot, is how when you exercise and your muscle generates so much CO2 with aerobic exercises, and how it drives the acidity in the blood. And when you generate so much of the CO2, then which side would that reaction goes? Can you guys type in the answer, like either go to the left or go to the right? With the reaction equation is written in that red blood cell. I give you guys 5 more seconds because it's a pretty easy one. Alright, so the reaction, as you all say, is it goes to the right. And what in the end of the day you will obtain more of that um, proton species. Then you have to think more steps now. Like, will it drive the acidity of the pH value? Will it goes down or goes up? After you evaluate which direction of the reaction could go, so more often the questions on MCAT is not gonna be asking you which direction it will go. It's often talking more about how you can make more steps in terms of that cognitive process to get to the right answer. Which here I might ask you guys, like, would the pH goes down, would the pH goes up? But in the actual exam, they might even ask you, will it goes beyond the normal level of the normal blood pH? And here we will work back to the same article that I showed you in the very beginning. Here it talks about the side chain of the histidine, the imidazole, and the pKa value are given to you in figure 2. And here's the questions. I will give you guys probably 1 minute to answer the questions. Okay, I saw most of you guys got A. And let's think about it. So when the species reaches equilibrium point, it's gonna be 50% of the cation, which is on the left, right? On the very left of figure 2. And 50% will be on the right, which is the neutral imidazole. When it is 50% left and right, that is given that that pKa value is exactly equal to the pH value. And the pH value indicate how much of that proton is available in the solution, which here is blood, right? And if the pH value, the lower the pH value be, the more proton is available to protonate the imidazole. However, here we see that the pH value of normal blood is higher than the pKa, which is 6 to 7. So that means that it actually has less proton available to even reach to the 50-50. So in that case, the cation actually would lose that proton on itself. So instead of A, the correct answer is actually neutral. Anyone having like confusion about this question?
Yeah, I'm having confusion. I don't see why it would be neutral.
Let me see. So can you, I just wonder how you got to A.
I got to A because I remember when we were talking about in the last slide with acids and bases, we associated acids with anions and bases with cations. So I just assumed that a pH of 7.35 or 7.45 would be a little bit more on the basic side. So I would assume that it's a cat, like it'd be more cationic.
Oh, okay. So let me okay. I wonder if I can. This is actually a little bit difficult. I don't know if you guys can see it actually. Let me see if I can type it in the chat to better answer. So when the pH is equal to pKa, both of the species, there will be 50% of that imidazolium cation and the neutral, and 50% of the neutral. So here it is, the cation is actually the protonated form. So the imidazolium on the left is the protonated form. So it is the acid. And when it donates that proton, so the HA, when it donates the proton, it becomes neutral. The imidazolium Could you guys see what I typed in the chat? So when that protonated form donates the proton, it becomes neutral. And given that when pH is equal to pKa, you got 50% of the cation, and then you got 50% of the neutral. And the neutral form, the neutral imidazole, is actually the conjugated base. So here we are using the concept of Bronsted-Lowry, the protonated form, as the acid. The basic form, the basic conjugated form is actually the deprotonated neutral imidazole. Okay, so if you think about the equation that you have right here, if you have less proton in the solution, would the reaction go to the left or to the right? Would it go to the protonated form or deprotonated form? Because it is less than what the equilibrium would be. So it will go to, let me see. If it is less than the solution at the equilibrium, it will go to the right? Because the right produced the proton, and right now the proton in the solution is actually less than the equilibrium. Does it make sense to everyone or no? Should we come back to it in a little bit after we go over other things? It makes sense to you, Sarah? So here it is confusing because the cation is actually not the base that you might think about just because they are positively charged. You have to think about which one is protonated, which one is the acid. But we will definitely come back to this afterwards. And the next question talks about, also related to the concept of Le Chatelier principle. Here you have multiple pKa value, which is very common in amino acid. Here we wanted to focus on what the entire histidine molecule be. the entire charge of that histidine molecule be when the pH is equal to 1.0. So recall that pH 1 is very low. And what does it indicate about the proton concentration? And what direction would it drive that protonation or deprotonation? So here I will give you guys 1 minute so that we can catch up with the passage. Okay, so let's see. We got A, we got B, we got D. What variety of answer? That means diversity, you know? Okay, so let's see. Again, equilibrium constant indicate the state when it is at equilibrium. The pH is talking about the solution itself. Whether there's high concentration of proton, low concentration of proton, if that concentration of proton is more than the equilibrium, it's gonna protonate a lot of them. However, if the concentration of the proton is way too low, then it would drive it to another way, like a lot of them would become deprotonated. So here, if you look at comparing the pH and the pKa value, for pKa1, it is at 1.82, and the pH value is even lower than the equilibrium. So that means that there's so much proton that for that carboxylic side chain is gonna be protonated. Okay, so then I would write down that for the side chain, the pKa1, that reaction group would get protonated. So that that negative charge right there, once it get protonated, will still be there? Probably not. So that negative charge will goes away, becomes 0. And now we look at the pKa2. The pKa2 is at 6.0. And 6.0, again, it is much higher than the pH. That means that there's so much proton right there that is likely to protonate that state. And by that figure, we already know that it's likely to be protonated. So it's gonna be probably a positive charge right there. And then the third one, it is the NH3. And the NH3 get protonated or deprotonated at the pKa 9.17. Again, is much higher than the pH as indicated. That means that this NH3 would likely to be stayed as protonated. So with the third functional group also be a positive form, then we kind of calculated the first one would be neutral, 0. The second one would be +1. The third one would also be +1. Therefore, the correct answer would be +2, which is A. Why doesn't it becomes +2 for the third one? So then we'll have to think about the structure. For N, nitrogen, we have 5 electrons on the outermost, right? So think about 3 of them are already bonded to the hydrogen, meaning 1 lone pair right there. And then the 4th electron bonds to that carbon, which is to the center of that molecule, and then it loses 1 electron more. So one of the proton will actually take up the lone pair of the nitrogen, and therefore that nitrogen can only have a +1 charge. And I kind of wrote down how I kind of think about the relationship between pH and the pKa here. Let me double check one last thing, and then we'll protonate it. Okay. So when the pKh is larger than the pKa, there's more proton. The pH larger than the pKa, the proton concentration is less than equilibrium. Therefore, deprotonation takes place. Whereas when pH is lower, it means that the proton concentration is more than the equilibrium. Then you protonate that species. So the person who asked about the why it did not become +2 for the third one, I suggest you can look at the structure, the Lewis structure of ammonium ion. It probably will help answer your question if you still don't understand. So again, minimize the amount of equations that you have to remember. Really, you can boil down the or the K, the equilibrium constant, to single one thing, remembering where does the reactant go, where does the concentration of the product goes in terms of the denominator and the denominator, and then relating the pH and the pKa is the same for pOH to pKb, because the way that they calculate is the same. All the pH, P whatsoever, they calculate the same way. If you remember one, you are able to remember everything. So try to reduce the number of equations that you have to remember. I actually prepared other questions, which this one we're not going to go over because I wanted you guys to practice on the passage. But when you guys got the slide, I hope you guys can try, because these kind of plots are gonna be shown up pretty often. And next week, they're probably gonna go over this titration as well. So I encourage you guys to practice more. And I will hand over the time for Sim, and I will stay behind to answer any additional questions.
Okay, thanks, Isabel. So I'm going to send the passage to you guys, and I'll give you 10 minutes to do it, and then we'll go over it. So here it is, and let me know if you're able to access it.
It's the same link. I'm sorry.
Yep, you're good. We'll go over it in 10 minutes. let us know when you're done in the chat and we'll go over the problems. Okay, so for the sake of time, we're going to start going over the passage. And if you're not done, you can still watch us go over it because you can watch the recording and go over it later as well. So how did you guys find the passage? I can go over it quickly too. So here, it was from the Khan Academy passage, and they talk about the phosphate buffer system, and they tell us, which is pretty nice, which one is the acid, which one is the base, and they also give us the equation. I would also know this because it does come up often usually, and sometimes they're not nice enough to give it. And then they also tell us if hydrogen ions enter, they're consumed, and then the equilibrium shifts to the left. If hydroxide ions enter, it makes more of this, and it shifts the equilibrium to the right. So this is how the pH is allowed to not change that much, even if acid or bases are added. And they give us the Ka and how to find it. And they also give us the Henderson-Hasselbalch equation, which you should already know and memorize, so if they don't give it to you. And they give us a table. So we'll look at all of that during the passage. Okay, so question 1. I'm going to go over these. Feel free to stop me if there's any questions about it. So which solution has the smallest ratio of conjugate base to conjugate acid? So for this equation, what should be going off in your head is that you need to have a ratio, and that should let you know that you need to plug it into the Hasselbalch equation. So doing that, we look at the table that they give you. So if we have NH4Cl and NH3, we go to the table that they provided and right here and plug those in, okay? And then we are able to solve for the ratio. And then we do that for all of them, and then you find which one is the smallest ratio. So the smallest ratio is just going to be subtracting this side from this side. So 4 minus 3.19, 5 minus 4.74. And like that.
Sorry to interrupt. I'm just curious, what made you know that you have to use the Henderson-Hasselbalch equation to address this question?
So I know it said ratio, and ratio is like a fraction, and the only equation that had the fraction was the Henderson-Hasselbalch equation. So this is a ratio of the base and the acid.
Okay, thank you.
Oh, sorry, let me go full screen. Yeah, but this is the ratio of the base to the acid, and this is how you can know. And then you just subtract the pKa from the pH, and that leaves you with the ratio. Okay, number 2, how can the amount of hydrogen phosphate ions be increased in the phosphate buffer? This they mentioned in the paragraph where they said that when you increase hydrogen, you shift the equilibrium to the left, and versus if you increase the hydroxide ions, you increase the pH to the right. So if we want to increase the hydrogen phosphate ions, we're going to have to increase the amount of hydroxide ions entering, because according to the phosphate buffer, it's going to shift to the product side, and we need to increase the hydroxide ions. Does that make sense? Okay, question 3. So now we're given that we have an enzyme and it needs to be in an alkaline environment, which is basic. So which pair of compounds is going to help maintain this enzyme? So according to table 1. So we would go to table 1 and see which one is best suited for a pH in a basic condition. And then doing that, we would try to look at pH levels greater than 7, and the only one that had that, I think, was around pK of 9.26, which would be NH4Cl and NH3.
Could you repeat how you got that answer? Because, so how did you conclude that it was C? Because I knew that we needed I understand that we need an environment that it's alkaline, so we want something that's basic. So
yes.
So what is the
so looking?
Oh, okay. So
yeah, sorry. Go ahead.
So I'm assuming the higher the pKa value, the more basic an atom is.
Mm-hmm.
Okay.
Yes. Yep. So that's what we wanted to look at, and here we saw that the pKa value was 9.26 for here. Does that make sense?
Yes.
Okay. So question 4, if we're given that the amount of dihydrogen phosphate ions outnumbers hydrogen phosphate ions 100 to 1, what is the pH? And then again here, we're given the acid and the base. We're going to plug it into our Henderson-Hasselbalch equation because we're asked for pH. We are given pKa as well. So we're given the pKa is 7.21 or 7.21. And then we're given this equation, which is 1 over 100, and then you have to just subtract it. And make sure that you know your log rule. So if you are dividing a fraction and it's smaller, it's going to be negative. And that's how we get 5.21.
I was going to ask, would it be a valid way, because this is what I did, just to knowing that they told us that H2PO4 minus is more acidic, and then the HPO4, and that, so like knowing that, you would know would be more, like it would have the lowest pH?
Plus, yeah.
Okay.
Yeah, exactly. Yeah, that's how they also say it at the bottom, that you know that having more dihydrogen phosphate ions and it outnumbers a hydrogen, meaning it's going to be acidic. So the pH is going to be less than the pKa, and the only one that had that was 5.21. I just wanted to make sure you guys understood how to also plug it into the equation, but please definitely use all of the knowledge, and if it helps you figure it out faster using it that way, please do that. Okay. So in the passage, they told us it was around 7.4, yes, pH. So in order to do that, we have to find the we have to convert the Ka to pKa, and then the only one that comes close to that is with the pKa of 7.49, which had HClO and ClO minus from the table. If you take the negative log of the Ka. Do you guys have any other questions on this passage? Okay, if not, thank you guys for coming, and feel free to email us with any questions. We'll upload the recording later and also put the slides up later. So thank you so much for coming today.
Thank you.